report. Our team is engaged in Lozhkin in treatment of different metallic structures. First of all, I want to tell about equipment that we use for treatment and for measurement, and then about different patterns of treatment for specimens with notches. And after that, it went about numerical model. Somewhat about what is a Lozhkin and what equipment we use for it. Lozhkin is an effective non-contact method for treatment of different metallic constructions. It allows to form a residual stress field that will improve fatigue life and corrosion resistance of metallic constructions. Due to the shock heating, short high energy pulse generates the shock wave, which propagation leads to creation of compressive residual stresses. If we speak about this process, we can divide it into 4 phases. Initially, other pulse affects the surface of structure in resting water, and with a layer that is less than 1 micrometer is vaporized. And in the second phase, steam continues to absorb minor laser energy, and it's ionized into high pressure plasma. When at the first phase of high pressure plasma propagates into the material in the form of shock waves, after that we can form residual stresses by means of inhomogeneous residual strengths. As I said, this method can improve fatigue life and corrosion resistance, and if compared with other surface treatment techniques, disadvantages is one that we can treat and improve surfaces for geometries with very difficult structures, and the depth of residual stress that we can form is higher. This is the installation that this is a picture of installation that is located at our university in our laboratory that we use for treatment, and it has a wavelength of 164 nanometers, and frequency of pulses is 5 Hz. We have different objectives, and it can allow us to make different spots. We have several lenses with 2 millimeters in diameter and 2 square spots 1 to 1 and 3 to 3 millimeters. And one more equipment that we use for measurement where that pressure can our laser installation make. We use photonic Doppler velocimetry. It can estimate the pressure that we receive by means of measurement of the velocity of this phase of specimens. For these measurements, we use several specimens with different thickness. The diameter of this specimen is 20 millimeters, and the less thickness is half of millimeter, and the maximum thickness is 1.4 millimeter. We measure the velocity of this phase. This is picture. And when after that, we recalculate it in the pressure. As we know the longitudinal wave velocity and the density of material, so we can estimate for different pulse energy with we have experiments for 4 energies, 2, 4, 6, and 8 joules. And after that, it corresponds to this power density energy. We receive pressure, and So we can estimate how much time pressure is increased and the pop of body pressure, and how much time pressure decrease. So we can estimate duration of pressure path. And it depends, as we established, it depends on materials and different spot size. It was interesting for us. And we speak about specimens that we treated. It was specimens with a notch. We used 3 different patterns of treatment. First, but we treated only surfaces. The second pattern we treated the notch. Not shown was explained. And for that pattern, we treated all surfaces. For this experiment, we used square spot, 1 millimeter. Pulse duration for our installation is 10 nanoseconds, and energy that we used was 1 joule. After that, we measured the field of residual stress using hole drilling method, and we see that the maximum value of compressive residual stress is about 600 megapascals, and the depth is about 900 micrometers. That we have 2 experiments on a several hydraulic machine with retention load equal to 10 kilonewtons. We examinate base specimens without treatment and different patterns of treatment. And we understood that the first pattern didn't give good improvement, in particular compared with the second and the third part, where tick life was increased about 10 times. After that, we decided to use numerical simulation to estimate what residual fields we received after these patterns. To speak about numerical model, we use this Lozhkin package that is used for dynamic problems. And can help us to estimate the fields of residual stress. And the numerical simulation can be divided in several stages. At the first stage, we investigate material parameters. We used the Johnson-Cook model for describing dynamic impact of our laser installation. And also we after that we when we received parameters of the material, estimated parameters for Johnson-Cook model, and now parameters of treatment. We solved dynamic problem for first plastics wave accumulation. After that, we solved static problem and received residual stress formation. After that, we verified our numerical results with experiment that we received in hole drilling method. In mathematical statement in equations, our numerical problem can be written as this. We solved this problem only as a mechanical problem without formulation of ablation of the material and plasma generation pressure pulse we received from PDV data and applied is as a pressure on the surface of our specimens. After that, we compare our numerical results with whole drilling method, and we see that difference is about 10%. We have a good agreement numerical and experimental results. This is a full distribution after laser shock pinion in different patterns. When we treat only surfaces, when we treat not, and when we treat all surfaces. After that, we decided to estimate the field of residual stress after tension. As I said, fatigue tests was at the load 10 kilonewtons, and for different patterns, we try to estimate each load will correspond to base specimen and for treatment specimen. For first pattern, this load is equal to 11.7% because we decided that the crack and degradation of material becomes from not from the surface, and we try to estimate which residual each stress will respond to base specimen. And for that pattern, it is the level of load is a bit increased, so we couldn't see fatigue-like improvement for this pattern. For the second pattern, when we treat only the notch, is great. For the second project was 19 kilonewtons, and for the third part, it was equal to 16.5 kilonewtons. So for the third pattern, we decided to estimate fatigue life in fatigue tests, not only in numerical results. And as I showed in the beginning of my presentation, we estimated fatigue life for base specimens, and it was this. And after that, when we increase the for treated specimens of pattern number 3, we have the same fatigue life as for base specimens. So we proved our thoughts about this. So this is stress field distribution for base and for treatment specimen. So by means of numerical modeling, we can estimate in which level we can increase load for different patterns for this form of specimens and with such knowledge. So that's all what I want to say. If you have any questions, I would like to answer.